everybody. So as the slide says, I'm Nevo. This is Barak. We are so excited to talk to you today. We've been going to Intent since the beginning. We love it, and we thank you so much for coming to the talk. We are super excited to show you the research that we've conducted. And let's get right into it. Breaking your beloved cubes etcd for smiley face and dollar signs. Okay, so today we are going to be going over what is CNCF, what is etcd, why is etcd everywhere, what's the impact of it is, a vulnerability we found a weak SSRF that we escalated into a stronger SSRF, exploitation, and privilege escalation that we've conducted with it, and a note to end on. So let's jump right into it. Okay, short word on CNCF. CNCF is Cloud Native Computing Foundation. It's owned by the Linux Foundation. It's backed, managed, and observed by the top companies, tech companies in the world: Apple, Microsoft, Google, Yandex. Every single one of them has some slice in CNCF. Its purpose is to be the watchdog of the cloud ecosystem of frameworks. So there are only 29 graduated projects so far in CNCF. Among them are the biggest in the tech stacks: Kubernetes, Istio, Cilium, TiDB, etcd, and etc. Specifically, incubating projects, it sounds like they are not as mature. Some of them are very, very mature, and they exist in every tech stack: gRPC, OpenTelemetry, Thanos. So many incredible projects that are not yet graduated. So being an being a CNCF graduated project is a big deal. Okay, etcd, what is it? etcd is a key value storage, simply as that. Data comes in, data goes out, you can read, write, modify, pretty much it. So why is it so important? etcd is very accessible. It can be secure, can be. It's super fast, and it's very reliable. So it was elected and adopted by Kubernetes to be the main data store used for synchronizing clusters and the nodes between them, and making sure everything in the configuration and runtime is synchronized. A short note, etcd-ctl is only a client-side binary. It's used to modify and affect the state of an etcd server, either locally, maybe remotely. That's it. Okay, so why is etcd different for Redis, for example? etcd is distributed differently using the Raft consensus algorithm, and it's super reliable. What I mean by that is that etcd uses what's called members, which is practically nodes. So when a node is added, it's synchronized into the cluster. It's synchronized, it receives all of the keys, and it becomes part of the consensus using a quorum. So when a member crashes, being corrupted, network outage, whatever, house on fire, if a member is shut down, the data persists, the cluster keeps on going, and the cluster is not totally affected and doesn't crash and burn because of one down member. So it's a very, very strong concept. Okay, so what's the issue? Everything up until this point sounds awesome. The issue comes when people and frameworks, mainly frameworks, cut corners. Specifically, many Kubernetes operators, for example, the K3s, which is the lightweight operator, which is very, very widely used, it's so easy to make a mistake and misconfigure it. For example, in K3s, it's very easy to just, when you want to use an existing etcd data store, you just point to it and you give it HTTP and the port and the address to the etcd. But if you point to an HTTP and not HTTPS, it doesn't upgrade. It just takes it insecure without any TLS certificates, and etcd by default doesn't require any authentication. So the cluster is joined. It's totally healthy, everything is fine, but everything from its lifeblood to its configuration to its synchronized data in real time is exposed to the etcd. Even worse, so many frameworks, so many important frameworks and packages configure etcd without any TLS certificates, without authentication, no role-based controls, nothing. Even worse, let's take, for example, TidyB. TidyB is a very, very widely used package. It's used to create databases which are distributed for high velocity and high volume of data. Very reliable, very widely used, very susceptible to attacks. Because TidyB is actually configuring its own etcd. It starts it over any interface to the internet on 0000 without any TLS certificates. So essentially, if the port is accessible, TidyB exposes your cluster configuration and everything relating to it. There are so many packages that are being affected by this issue.
Great. But we are all here for vulnerabilities, right? So let's talk about that. So after discovering this amazing etcd package and investigating a little bit more, we come to realize that there is some feature that is called the members feature. So when you have this etcd client that communicates with the etcd server, it can also add itself as a peer member. And it announces its peer URL to the server itself. And when it sends it to the server itself, well, guess what happens? Yeah, so the server reach out to this URL, exactly. So it's really a textbook SSRF out of the blue, like out of anywhere in the first lines of code that really investigate this peer URL. And this is the first starting point that we've discovered during this thing. Also, it checks some compatibility of new membership. I don't know, it's a feature for SSRF. So that's what I remember about that. Also, this peer URL is not validated at all. So that actually means that you can send to any URL, also local network, but as you can see here in the code, it's limited by the URL itself after the path. So yes, unfortunately, it's a very limited SSRF. So no full path, no query parameters, nothing that we can really control protocol, and it's really strict to only host and port that we can decide, and after that /version automatically appears. So we try to figure out, and as usually researchers do, they try to find some weird kind of shenanigans that inside the RFC and the source code and such. So of course, let's do one of the most maybe trivial things, but not the most of them. Investigate this library, right? Investigate net HTTP and see what we can do with that. So investigating a little bit of this code, we thought to ourselves, well, why not making a redirect? What will happen if we just redirect the request that is getting from the etcd server to the client, or what's supposed to be the peer URL client, and redirect it back to other servers or other platforms? Would it tag along? Well, the answer is yes. And you need to actually enforce the check redirect function in order to it not to follow any redirection. So by default, the NetHTTP Golang library actually follows any redirections that is being given out there back. So we can, redirect it to any path that we want to. And that's really escalated the flow itself. So let's recap the SSRF flow from weak SSRF to unlimited instance SSRF. Yes, it's a blind SSRF. And yes, we're again talking about the huge amount misconfigured etcd servers that we've seen with no authentication. But in these scenarios, we've seen that we can add peer member. This peer URL is being sent under the protobuf inside the Raft protocol. And we use the etcd CTL to send that. The etcd server triggers the request. We redirect him to any URL that we want, and then we get arbitrary SSRF to any path that we want to. Okay, great. And then we reached out to etcd security team, and we were quite astonished by the response. They were like, okay, yeah, we know that it might code SSRF, but like, it shouldn't be a problem. Like, who opens up their etcd servers out there with no authentication, with no TLS credentials? Like, it shouldn't happen. Famous last words. So what you can see here is like it's Chance's search, very trivial, just checking non-authenticated of disabled instances of etcd servers, and we found thousands of them. So by that I mean like more than 7,000 of etcd instances. Some of them belong to the frameworks that Nevo was talking about earlier, and some of them completely different from K8 Kubernetes clusters that are like misconfigured in a sense, and have this no TLS and certificate out there exposed. That shouldn't be a big problem, very big problem to say at least.
Awesome, thanks. Okay, so let's check out how small is this problem exactly. So we are creative people overall, I think. So I'd say we can test it out. We can leverage this full arbitrary server-side request forgery, and we can create requests and leverage maybe existing CVs. Maybe we can create a request to an susceptible log4shell vulnerability, maybe Spring4shell, maybe other 4shells that you have. But there's something much, much cooler than using and leveraging the arbitrary SSRF with CVs, is leveraging the SSRF with an out-of-the-box, clean installation, default configuration of an existing package, widely used package that comes in API 6. API 6 is a dynamic, real-time, high-performance API gateway. It's better than Kong, it's better than Nginx. That's why they claim at least. They have so many users, so many live instances. So what's the issue here? What's the problem with the cloud-native API gateway, or at least the self-proclaimed one? So starting off, API 6, right off the bat, it starts. Its configuration is entirely stored within etcd. Okay, kind of a weird decision, but it makes sense because it's highly available. So this is a clean installation of API 6 within an etcd instance. You can see it has some rules, it has some configuration, the plugins, the environment variables. Okay. Another thing to notice here is that etcd connects API 6 connects to etcd insecurely. By default, this is straight out of the box. It connects without certifications, without any TLS, and without authentication. It is possible to synchronize API 6 to connect to etcd with a TLS certificate, but you have to go out of the way and find in the niche documentation the specific parameters that you need to use. You must generate them for yourselves because they wouldn't do it, such as TidyB didn't, and many, many other packages have not. So they just assume that you have the knowledge and expertise and the time to make sure and step out of the way to ensure you are communicating over TLS. In reality, it's not the case. A much, much more fun for us, dangerous for people issue is the script tag. Nginx, specifically API 6 over Nginx, what it does, it stores routes. You can configure just routes from point A to point B. It's a reverse proxy. It's what it does. And you can define for each route within the gateway a script to be run whenever a route is triggered. So if you think this is sandbox, this is a security issue, no. This is a huge security issue. You see, it allows module loading. It doesn't sandbox. It's not a feature. They don't do it. They allow you to run Lua code arbitrarily directly on the machine. They assume nobody would have access to the etcd instance, but they're wrong. OK, so let's take everything we've been talking about and combining it to one full chain attack. We very easily find an etcd instance exposed to the web. We've seen thousands of it. You can still find them very, very easily. Of them, it's easy to find API 6 with these instances because API 6 is reliant on etcd, so it can't come without it. OK, so we can access the etcd remotely. We can add a malicious route directly to its configuration, which is accessible to us. And this route will contain our very specially crafted piece of payload, which allows us to run command line shell commands on behalf of the server and control it however we like. But there's a big issue here. Many times, in most cases, the API 6 gateway is not outward facing. It's not meant to be able to be triggered remotely. So what do? We define a very, very wide route. It receives any path on any method that runs the code on our behalf, and we trigger it ourselves, even without access to the API 6. So how we do that? We leverage the SSRF that Barak explained. We take a new endpoint, and we just make sure to include a new member to the etcd, and we direct it into the local network where the API 6 is configured on. OK, let's see it in action. So what I'm about to show here, you're going to see a clean EC2 instance. It only has the default SSH and the only primitive and exposed etcd instance. Awesome. I'm going to show how a clean installation, out of the box, latest version of API 6, and an etcd, also out of the box, clean, not specially configured, just open and exposed port directly as it comes from the vendor, and we're going to show what we're going to do with that. So we're going to start off by creating a listener to show where we are going to receive our output. Left side is the API 6. Right side is the attacker machine. It's empty. And we include the malicious route in it. Now we're going to see nothing yet has happened. It's only a route. Nothing is coming to the receiver end on the listener. Let's trigger the SSRF. What we see now is a non-stop barrage of requests containing output from shell commands execution from the machine, returning to our listener. We can see it ran who am I, returned Ubuntu, and we see it used curl because we defined it to do so. Amazing. So let's take a second back. Let's introspect on what etcd security team said. Not a big issue. After showing them this and talking them continuously and helping them with suggestions of fixes, they said, OK, that's it. We agree to changing every single instance of HTTP net get in the code. They nullified the check redirect, and that should be the case, right? We'll see. Awesome. So thank you so much for coming and listening to our talk. Thank you.